Welcome to the third lesson of our fourth unit. Right now, you should have your Cornell-style note sheet in front of you. Draw those 3 lines. The title for this week is Natural Disasters. And the question we're going to try and answer right now is, where on Earth is it dangerous to live? And as we go, we're going to consider these key questions. So as always, you don't really need to write these down. This is more of a thinking slide here. So read each one, ask yourself if you know the answer already, but also be listening as we go through and see if you can answer them as we go. So we should know where do natural disasters occur? What are the different types of volcano? What is elasticity and how is it tied to earthquakes? Is there a difference between a subduction quake and a transform quake? And then finally, how do we measure an earthquake? So this is a little bit of review for you, but each plate boundary is responsible for its own geologic natural disasters. And even though they do similar things, the causes are not the same. And so we're going to only focus on 2 types of geologic disasters with this lesson. They are volcanoes and earthquakes. Now, there are other ones, landslides, tsunami, sinkholes, you name it. There's more, but we're going to focus on just these 2. You do want to make sure you are writing this next line down where it says, ultimately, all the disasters are caused by the convection of the magma. Because remember, without the convection of the magma, the lithospheric plates would not be moving. And it's the movement of the plates that causes all of this. So keep that in mind. That's worth noting. Let's start with volcanoes. First thing you need to know, 2 types of volcano. One that is trying to kill you and one that is kind of safe to live next to. It's not safe in that you can let it get lava on your body, obviously, but it's safe in that it doesn't explode. So what I would do, and I strongly recommend this, is to draw the pictures because there will be images that you're going to have to identify on future assignments. So please make sure you draw the pictures. There's a shield volcano on the left and there's a cone and composite. Those are kind of similar or kind of the same thing on the right. So draw the shield on the left. You don't necessarily need the labels, but just the fact that it's a flat volcano. And then on the right, you don't need all the labels again, but you could draw the fact that it is very steep. It looks like an upside down ice cream cone. And we're going to get into that. So we'll start with shield. The picture you're seeing there on the right is a lava lake in a caldera of a shield volcano. Shield volcanoes usually happen in one of 2 places, either a divergent plate boundary where the plates are separating, or at a hot spot in the middle of a plate. And the best example of that is Hawaii, the state in the United States. It is created by upward convection. Now, think about this. If the magma is convecting upward, meaning it's moving up towards the crust, where is it coming from? And the answer is usually deep in the mantle near the core. As we know, the core is the hottest layer and it's about the temperature of the surface of the sun, actually maybe a little bit hotter, and the sun obviously is very hot. So the lava coming up or the magma coming upward from there is going to be very, very hot. Now, because it is very hot, it doesn't stick to anything. It flows like water. And so what you get is you get very flat slopes on a shield volcano. By the way, that's how it got its name, was how flat it is. From the air, it looks like a warrior's shield. But the lava is very thin and watery. And that's mostly caused by 2 factors. One is the silicon in it. Don't really need to know the chemistry of it, but you do need to know that it's very hot lava. It runs like water. And so the thing I want you to think of is you cook a marshmallow over a campfire. The warmer it gets, the more watery it gets, or the more thin it gets. If it's cold, it sticks a lot more. So shield volcanoes don't really explode. Think of it as a pot of boiling water on the stove. A pot of boiling water will bubble, but it's never going to blow up like a huge explosion that knocks the pot off the stove or anything like that, as long as you don't have the cover on it. The water just boils. And so that's similar to a shield volcano. Most of the time, this is actually fairly safe to live next to. People in Iceland live next to volcanoes. People in Hawaii live next to it. Obviously, if the lava starts pouring out of a fissure near your house, you have to move, but it doesn't blow up. It doesn't usually take you by surprise. And then shield volcanoes are the home of mild earthquakes, because when the lava pushes up, it does kind of move rocks around and that causes earthquakes. But these mild earthquakes are not dangerous. They usually don't damage anything. And so we have a video here to show you about shield volcanoes.
Hawaii's Big Island. It's a tropical paradise of palm trees, sand, and sun. But it's even hotter than it looks. In the heart of this island is Kilauea, the world's most active volcano. Kilauea's lava, and lava from the island's older volcanoes, Mauna Kea and Mauna Loa, built this island, and it's still growing. It all started here, deep below the bottom of the ocean. A hot spot in the Earth's mantle sends molten magma through the Earth's crust. Over time, lava flows on the Big Island have produced a mountain taller than Mount Everest, if you measure from the sea floor. All of the Hawaiian Islands were formed in this way. A volcano is one way that the heat inside the Earth is released. The heat moves in the form of gushing lava, which flows freely in swelling waves down the mountain, and in this case, into the ocean. Kilauea is known as a shield volcano because of the way its fluid, basaltic lava builds up layer upon layer, spreading out in the form of a shield. Lava from Kilauea flows freely because it is low in silica and its temperature is high. As the lava flows, anything in its path goes up in flames. Kilauea's current eruption began in 1983 and shows no signs of stopping. Its lava hardens into acres of new land every year. Kilauea's volcanic power comes from a hotspot in the Earth's mantle. But shield volcanoes are not the most common or the most explosive kind of volcano.
All right, so if shield are all those things, this one right here is exactly the opposite. So this is a type of volcano that basically there's two subtypes, and they are cone and composite. Basically, a composite is a big cone. The first thing that happens is a cone pops up, and then as more layers get put on top, it eventually gets and grows into a composite volcano. But these ones come from subduction. And as a result of that, we get these violent explosions that you see in that picture. So make sure in your notes that you have the fact that it's a subduction boundary, that it's created by the melting of an oceanic plate. As it descends into the mantle, it increases in temperature, which lowers its density, and it rises to the surface to try and find an opening. The magma is colder, though, than a hotspot or a divergent. The reason why is the magma is not coming from the core. It's now coming from the surface. And I think it's pretty obvious, but the material at the surface is much, much colder than the core. The core is as hot as the sun. The surface is cool enough for, you and I to live on. So as a result, the lava is very thick and sticky. It's viscous, which is another way to say its thickness is high. And as a result, it pushes up and gets stuck. And the result of that is you get really steep slopes. And the eruptions are violent explosions. So basically what happens is the lava is kind of like bubble gum. If you've ever blown a bubble with bubble gum, you know that you kind of form it and then you start blowing air into it from your lungs. And then if enough air goes in there, it pops, right? So a volcano is very similar to the bubble gum. It gets stuck, all the lava gets stuck inside, and more and more lava gets pushed up there, and gas and all sorts of stuff get pushed up in there until literally the mountain just can't take it anymore and it blows itself apart. The Mount St. Helens eruption in Washington State, the side of the mountain literally exploded. It just ripped off the side of the mountain. It just couldn't handle that pressure anymore. Now, these volcanoes are extremely dangerous. They are far different from shield volcanoes. They are responsible for many deaths throughout history. Some of the worst volcanic, in fact, the worst volcanic eruptions of all time, including the one in Italy called Mount Vesuvius, which you will learn more about now.
Mount Vesuvius, outside the city of Naples in Italy, is an example of a composite volcano. Composite volcanoes alternate between quiet, and extremely explosive eruptions. It sits near the boundary of two of Earth's tectonic plates, occupying a weak spot that lets magma from the mantle rise to the surface in a very dramatic way. On August 24th, 79 AD, an enormous chamber of magma far under Mount Vesuvius burst through its cone. The mountain's peak literally blew off. The thriving Roman cities of Herculaneum and Pompeii lay at the foot of the mountain. Over 50,000 people lived there. An explosive eruption called a pyroclastic flow hurled out rock, poisonous gas, and scalding ash. Buildings offered no refuge. They erupted in flames. In all, more than 16,000 people were killed. The volcano's victims were locked in time by the hot ash, their anguish preserved in molds left by their bodies. A column of smoke and ash hovered high above the city of Pompeii. Days later, rain fell, setting the ash like concrete and entombing the city until the 18th century, when the eerie scene came to light. Since this catastrophic eruption, Vesuvius has spit and sputtered lava and ash, but not with the deadly force of nearly 2,000 years ago. The next big eruption, though, might be just around the corner.
Now, you don't need to draw this. There's really no notes here. I just wanted to show you this. But take a look. The map on the left is the location of all active and dormant volcanoes that we know of. The red dots are the active ones and the yellow ones are dormant in that they haven't erupted in a long time. And we don't expect them to erupt again anytime soon. But if you look at it in comparison to what you see on the right side of the screen there, do you see how it's almost exactly the same as the outline of the plates? And so the result you want to kind of keep in mind here is volcanoes, with the exception of a few, which are hotspots in the middle of a plate, almost always happen on a plate boundary. And that information should tell you that to find a volcano, you have to travel or you have to be near a plate boundary. And if you're not, the likelihood is you're not going to be anywhere near a volcano. And you have to be a specific type of plate boundary, either divergent or subduction. So that was the purpose of this slide. A quick personal story. I've actually been to both types, shield and cone. This is Mount Hood in Oregon. It is still considered to be an active composite volcano. There's me standing on it on the left, and there is the drive up to it on the right. As you can see, its slopes are so steep, it's poking into the clouds there. You can't even see the top of it. In fact, when I'm standing on it, you still can't see the top of it because there's clouds all over it. But I stood on there. I will tell you the rocks are very sharp and jagged because it's from relatively recent explosions of the volcano, and it hasn't had a chance to weather it down. But yeah, so I've actually stood on top of a cone volcano. It's not actively erupting. That's not any gas or ash coming out. Those are clouds. However, I've also been to a shield volcano. It's hard to see in the upper left, but I'm the guy in the Hawaiian shirt that's squatting down, not the guy in the Hawaiian shirt standing up. That was our tour guide. But what you're seeing with that dark material is actually lava. The lava was getting up to this fence, and it started to push against the fence. And because it was so cold, it didn't melt the metal. But you could see the fence kind of bulging there from the lava that has since cooled. This lava flow was probably 50 years ago, he said, maybe 30, I'm sorry, maybe 40 years ago. And then on the right, we were on top of the Kilauea volcano, and we saw that crack in the ground that you can see. That was because the road is laid down flat, and the ground underneath it starts to shift and move, and it causes a crack. So much so that if you look at that sign, imagine you're driving along and you see that sign, basically increased volcanic activity, meaning be careful you don't drive into lava. So that's kind of crazy to think about. And then on the bottom left, what you're seeing there is when we were flying back to Oahu, because all the volcanoes are on the Big Island, we went to the Big Island, but then we had to fly home. Well, we flew home at night. And as we turned to go towards Oahu, we saw a really bright orange light coming out of one of the windows of our airplane. So I'm serious. I took that photo on the lower left. That is from my phone. And that's looking out the window of my airplane as we're flying back to Oahu. It's something to see lava on like a documentary or a YouTube video. When you see it in person, it's fascinating. It's very interesting. And I will tell you, it makes the whole sky light up orange because of its glow. So let's recap. You can make a little data table in your notes of this if you want. You don't really have to, but this might help you on your homework. But here's the differences between shield and cone. Shields are only at divergence and hotspots, whereas cone is at subduction. Shields are flat, cones are steep. Shields have thin magma, cone is thick, and then shields are not very dangerous and cones are quite dangerous. So based on the lava alone, what do you think this type of volcano is? This guy actually drove or flew a drone over an erupting volcano. Now, I know what you're thinking. You're probably thinking, oh, it's a cone because it has steep slopes. Yes, but what you're not seeing is that this actually is poking up from a caldera, a flat lava lake. So this is actually just based on the watery lava. This is a shield volcano. And I just want to point out, those are rocks flowing like water. It's insane to think those are rocks that have gotten so hot, they have melted. And now they're running like water. Now check out this one. This is actually a time lapse because it takes a little while for this ash cloud to show up. Watch this. I don't know if you saw that fire right there, but this is a cone, actually a composite volcano in the Philippines called Mayon. Let me see if I can pause it at the right spot. It looks like I can't. But anyway, let's go back. Let me see if I can pause it here. You can actually see a little bit of the fire. Look at that. As the eruption's starting, some of the lava actually kind of peeks out a little bit as the ash cloud forms. Watch. So that is a eruption of a composite volcano, obviously much, much different. And this is actually going many miles into the sky. As you can see, 61,000 feet. All right, moving on to earthquakes. Now, the first thing you need to know about earthquakes is, as the lithosphere moves because of magma convection, the rocks have a degree, meaning a certain amount of elasticity. What that means is when you bend a rock, and you can't because you're a human, but when the earth bends rocks, they have a tendency to want to go back to their original shape. And so as a result, they store energy. They keep all of the motion energy that goes into them and they store it or they hang on to it. And that's a term, or the term for that is elasticity. And so any place where the lithosphere then breaks or is even starting to deform is called a fault. So earthquakes always happen on a fault. Now, here's what elasticity means. Think of a rubber band. If I start stretching a rubber band, it resists to my pull, meaning it doesn't want to break. But if I pull on it, eventually, if I want to, I can break it and it snaps back and it potentially could hurt me. And the reason why is because the rubber band's trying to go back to its original shape. It's trying to go back to its resting shape. This is different than a paper clip. If I take a paper clip and I bend it, it doesn't resist me. Once I bend it, it stays bent. A paper clip has no elasticity. So that's very, very important. Please make sure you have that in notes, the word elasticity and what it means. Now, as a result, here's what happens in an earthquake. And you can see that image there to the right. And this is an example of a subduction plate. As the plate descends under the other, it starts to push the overriding plate down. It squeezes it and it causes something called stress. That stress is a buildup of energy that has gone into creating the bend that you can see there. But the rocks want to return to their original shape. And so eventually they do. You get some slippage or you get a break and the rocks go back to the way they were. And when that happens, you release all that energy. So all the accumulated stress is released. Here's a video on that.
Earthquakes are one of nature's most devastating events. They occur when a large buildup of stress within Earth's crust is suddenly released. Why does this happen? The answer is elastic rebound theory. Elastic rebound theory explains how energy is stored in rocks and released by earthquakes. This energy is transferred through rocks, causing them to move, which we experience as an earthquake. Earth's crust is made of giant plates of rock that float on the underlying mantle and slide past each other. The plates grind against each other along their edges in areas called fault zones. There's friction between the plates where they meet. This means that the plates don't slide freely. Instead, the rocks deform, straining until the stress is more than the rocks can handle. Suddenly, the energy stored in the deformed rock is released in the form of heat and seismic waves. The strained rocks suddenly resume their undeformed state. The whole process is called elastic rebound theory. It's like stretching out a rubber band. As increasingly more deforming force is applied, the band becomes more distorted. If the force continues, the band will break, and the stored energy will be suddenly released. Similarly, Earth's crust stores elastic stress that gradually builds up until its sudden release during an earthquake. Elastic rebound theory explains how earthquakes result in ground movement and why they most often occur on fault lines. Elastic rebound theory provides scientists with a model that allows them to forecast the probability and severity of an earthquake in a fault zone where they have sufficient historical information. The well-studied San Andreas Fault that runs through California is located where the North American plate slides past the Pacific plate. Researchers of the San Andreas Fault have determined that sections of the fault have accumulated sufficient strain to produce a major earthquake in the near future.
All right, so as a result of the elasticity of the rocks, we get two types of earthquakes. Let's start with the worst kind. This is subduction. So what happens with a subduction earthquake? Two plates are colliding, they hit each other. One plate slides down, but as it does, it drags the overriding plate with it. It causes something we call shortening. Now, what that means is basically the overriding plate used to extend a certain distance into the ocean, and it's being dragged backwards back towards itself, and it becomes shorter. As a result, it stores energy. That goes back to that elasticity part of it. During the shortening process, it also causes a little bit of uplift. And so as you can see on that diagram, it basically creates a mountain range right near the shoreline. When it eventually breaks and it goes back to the way it was, when it eventually does that, it can create huge earthquakes in excess, meaning above 9.0 in magnitude. The largest earthquake ever recorded was a 9.5 in Chile, South America. It shook the ground for 15 minutes, and it made the entire earth reverberate like a bell, and it actually changed the rotation of the earth. The earth that day was 1 or 2 seconds shorter, meaning it took the earth less time to spin one complete way around. It was crazy. If you ever want to look that up, you should. It's a fascinating amount of damage, or not damage, energy was released. It really wasn't that much damage because it happened so deep in the earth and it happened beneath the mountains and not a lot of people live there. So interestingly enough, subduction quakes can also create tsunamis. Tsunamis are big ocean waves. We're not going to get into that here, but they exist. And tsunami waves typically arrive after a subduction earthquake. And as mentioned, these type of earthquakes are responsible for the worst death tolls in earthquake history. So here's an example of a subduction quake near our state.
The Pacific Northwest is known for its towering trees, beautiful landscapes, and breathtaking coast. But it's what lies about 70 miles off that coast and anywhere from 300 to 10,000 feet below the ocean's surface that experts say we should really get to know. It's called the Cascadia Subduction Zone, a 620-mile-long fault that stretches from British Columbia to Northern California. It's where the Juan de Fuca plate is being slowly pushed into and underneath the North American plate. Right now, that zone is locked as the pressure builds daily. Geologists are well aware one day the pressure will be too much and that lock will break. When that happens, one plate will thrust below the other, generating one of the largest earthquakes ever recorded, a magnitude 9 or possibly even greater. The shaking will be felt for hundreds of miles from the coast all the way inland to Boise, even Sacramento. As one section of the ocean floor drops, so will the ocean water above it, creating a massive tsunami that will inundate low-lying coastal communities. It is a frightening scenario, and one geologists say could happen at any time. The last known Cascadia subduction zone megaquake struck in January of 1700, 319 years ago. Geological evidence shows these large quakes happen about every 250 years, which means really one could happen at any time. The problem, no one knows exactly when that time will come. But scientists are getting a better idea. They now believe there's a roughly 30% chance a destructive Cascadia quake will happen within the next 50 years. The question now, will communities be ready?
So this is the other type of earthquake. When you don't have subduction, you have typically a transform style earthquake. Now, with a transform quake, two plates are sliding next to each other, as you learned last week, but in opposite directions. Now, when the plates are locked in position and can't move, they start to deform or change shape, and they eventually release that energy. Now, the earthquakes made usually at transform boundaries are not as big as subduction ones for many reasons. The biggest one is not as much of it breaks or slips at one time, whereas a subduction quake can break for over 100 miles. So that's the biggest reason. The other reason is just not enough pressure can build up. Usually, typically, transform plate boundaries don't store up energy as long, but their magnitudes are usually between 6 and 8. And what's also interesting about transform, different than subduction, is they actually can cause breaks and cracks and faults on either side of them. And this actually creates other smaller faults, which can then have their own earthquakes. So in San Diego, we actually have the Rose Canyon fault, which is not connected to the San Andreas, but is caused by the movement of the San Andreas. Now, I want to stress, transform plate boundaries cannot make tsunamis. The plate movement is lateral. It will not make a tsunami. So if you see a movie where California's earthquake happens and a tsunami comes to California, number one, you can't have a tsunami go towards the fault. It's always moving away. So that's not right. And then B, California has transform plate boundaries, which could not cause a tsunami. Now, transform boundaries do cause a lot of damage. They topple buildings, but they also cause far fewer deaths than subduction. So definitely not as much to fear. Now, we still need to be prepared and you need to be aware that they exist and they can produce powerful earthquakes, but it's not quite as bad as the subduction. And here's a little bit about the San Andreas.
Thousands of faults weave through California like a spider web. Some have yet to be discovered. San Andreas is the most famous in California because of the damage it has and will cause. We are due for the big one.
The fault is not just one surface, right? When it breaks in a particular earthquake, you usually see one surface. But each different earthquake might move slightly different place, and you end up creating a zone that can be a variety of width.
We took a tour along the San Andreas Fault with world-renowned seismologist Dr. Lucy Jones. Here's what she says will happen during the next big quake.
Transmission lines, if the fault doesn't run through the tower, there's often enough flexibility that they can move and stay up. However, if it runs through the tower, it's a problem. These rocks could literally be in the air. I mean, this is actually not the safest. I mean, mostly I want to be outside with nothing to fall on me, but these big boulders here could literally be thrown in the air.
Geologists say the southern part of the San Andreas Fault is 100 years overdue for a major quake. A large earthquake on the San Andreas Fault could be catastrophic for major cities anywhere close to it.
It would have pretty severe economic effects. The shaking would damage thousands of buildings. A lot of people will die.
Tim McCrink is a geologist with the California Geological Survey and says even things in your home could be deadly.
If you have gas running to your house and your house breaks.
You can see this building is collapsed.
They don't know if people are still in there or if they...
Right? Something severe happens to the house. You break those pipelines. Now you're pumping gas into the atmosphere. It doesn't take much to ignite that.
We've passed the 100-year mark since a massive earthquake on the northern part of the San Andreas Fault. In 1906, an earthquake in San Francisco killed 3,000 people and caused fires that burned for 3 days. Half the city became homeless.
The fire probably did more damage to the structures and perhaps to lives than the earthquake itself. But the earthquake itself did a lot of damage. The city hall was brand new and was almost completely destroyed. We know it takes decades to recover from these things, and we know that just from the 1989 Loma Prieta earthquake. They had their 25th anniversary not too long ago, and the word that I heard from that was that they were just finishing rebuilding some of the buildings in Santa Cruz that were damaged by that earthquake.
And it'll take a while for help to come. We're pretty much at the center of the San Andreas Fault along Big Pine Canyon. If the big earthquake hit, all the roads around me will be impassable.
It affects everyone, and I don't know how you can't, to look at your landscape and say, why? Why not? I mean, why, how can you, just, it's very boring to just accept everything as being there.
The big one on the San Andreas Fault will happen at any moment. The question is, are we ready?
Now, you don't need to take notes on this. It's not something you're going to necessarily be tested on, except that you do need to know all of the other faults created by the San Andreas. So I don't know if you can see the yellow line that's labeled number 1 in the middle of this image to your right. That's the San Andreas. Look at all the other colors. Every single one of those other colors is a fault. Notice how San Diego actually has a couple right off the coast there. And there's actually one that's not showing you that runs through La Jolla and into like northern part of Mission Bay. That's called the Rose Canyon Fault. But the thing you need to know is there are about 200 faults in California. So if you think the ground under your feet right now is solid, I mean, it is because we're in San Diego, but for the rest of California, it is definitely not. Now, how do we measure quakes? You've heard of that term magnitude, or you'll sometimes be watching the news and they'll say it was a magnitude 2 or 3 or 4 or 6 or whatever. What does it mean? Well, there's 3 basic things that it can mean. Number 1 is the Richter scale. You may have heard of that. That's actually kind of an older one. It measures ground shaking, but that's not the most reliable thing because 2 places in the ground could shake a different amount. So the number 1 thing we used to use is the Richter scale. Now that got replaced by moment magnitude. Moment magnitude is a measure of how much energy is released. And how you calculate that is you basically ask yourself how much ground moved and how far did it move. So if I pick up a cup and move it 2 inches, it's not the same as if I pick up a car and move it 7 feet. Does that make sense? So moment magnitude is a little more accurate. And so when you watch the news today, when you hear about the magnitude of an earthquake, you're usually going to be hearing about moment magnitude now. And I'll explain why that matters here in a second. And then lastly, you have the Mercalli scale, which is a measure of something else called intensity. And it basically means humans react to it. They take a survey or they talk to people and they try to find out how intense the ground shaking was. But here's the thing about magnitude, and this is what you need to know. It increases logarithmically. Every single point jump doesn't mean like it's double it or a little bit more. It is a lot more every point jump. So for every 1 point jump, the ground shakes about 10 times as much, and then the energy goes up about 30. So if you go from a magnitude 3 to a magnitude 8, it's about 50 times the ground shaking, 150 times the energy, and it goes up from there. So instead of the ground, imagine on a magnitude 3, instead of the ground moving by 2 inches up and down, if you go to a magnitude 8, it is moving by 8 feet. So imagine the ground underneath you right now moving up 8 feet. That is taller than you are. You're probably between 5 and 6 feet tall. It's almost 2 of you standing on top of each other. And that's how much the ground would be shaking your house, which is an amazing number. That image over there to the right, if you want to draw that, you can. It just shows you the size increase from a magnitude 1 to a magnitude 2. And I have a video to help drive that point home.
When an earthquake hits, we're all pretty used to hearing about its magnitude. a 5.8 for the Virginia 2011 quake, a 7.0 for Haiti's devastating quake in 2010. But what exactly do those numbers mean? They represent the energy an earthquake releases, basically how powerful it is, and the numbers build exponentially. And that can be a hard thing to picture. That's why this animation is so handy. It shows just how big the difference is from one magnitude to the next. Each magnitude is basically 33 times more powerful than the last. That means a magnitude 7 earthquake is 33 times more powerful than a 6. So take a look at that 5.8 Virginia quake. It looked pretty small compared to those 6.9 quakes. But compared to that 7.7 Sumatra quake, it looks tiny. And it's all because of this exponential scale. It builds fast, by a factor of about 33 with every jump. So the difference between two magnitudes, between a magnitude 6 quake and a magnitude 8, is 33 times 33, or 1,089. Do the math, and a magnitude 9 earthquake, like Japan's catastrophic Tohoku quake in March 2011, is 35,937 times more powerful than a magnitude 6. Even though we've gotten really good at measuring earthquakes, it's still impossible to predict them. Scientists can't say when the next colossal earthquake will happen, but they do know that one will, and that it's important to be prepared when it does. For Our Amazing Planet, I'm Andrea Mustaine.
All right, so now that we're at the end of the lesson, ask yourself, do you now know where do natural disasters or geologically based natural disasters occur? Can you tell me the two types of volcano and what makes them the same and what makes them different? How does elasticity affect or cause earthquakes? Do you know the difference between a subduction and a transform quake? And then do you know how quakes are measured, including how the scales move up logarithmically, meaning they get exponentially bigger as you go? So what you should do right now, finish these last notes if you have anything else to write, and then put them aside, go do something else, come back to them, and see if you can do a summary of what you learned without looking at the notes. If you can, you're in good shape. If not, take another look at the notes and create a summary. You're not done until you have that summary done. And once you have that summary done, you can turn it in. And as always, I thank you for your attention.